Welcome to SFAP. I'm your host Neha, and today we have with us Professor Urbasi Sinha, who heads the Quantum Information and Computing Lab at the Raman Research Institute, Bangalore. Dr. Urbasi is an affiliate member of multiple international universities and has also been a Homi Bhabha Fellow. I could go on about her achievements, but we should hear them from her herself. Let's welcome Professor Urbasi here. Thank you for joining us.
Thanks a lot, Neha, and of course your entire organization for thinking of me as someone you could talk to. So thank you.
Today we are going to talk about quantum communication with you and the rise of India's quantum computing era. So to start with, Professor Urbasi, could you tell us about your motivation to study physics and specialize in quantum? How did you end up sort of choosing this path, and when was the first time you decided to make this your career?
Yeah, so I mean, when I was in my undergrad at Jadavpur University in Calcutta, quantum mechanics used to be one of the most, favorite subjects for me and many around me, actually. It has always been a very intriguing thing to learn. And so in some sense, but that was at a theoretical level. But then when I went for my TRIPOS, which is a master's in Cambridge University in UK, the first experiment that I was, I sort of signed up to do had to do with Josephson effect, so making a very fine tip of niobium and actually being able to measure fundamental constants with that. And so that was a very fascinating experience because, the precision level of that experiment was something like 1 part in 10 to the 16. So it's a very precise experiment. And so that is when I think the excitement started for, doing something in the precision domain, I would say. And this followed, I did my master's thesis project also on superconductivity using Josephson effect, but something called SQUIDs. So these are two Josephson junctions in parallel, and it can be used to make very high precision magnetometry applications. And so something where you can measure signals from the human brain and things like that. So again, something which further, consolidated my, interest in pursuing experimental research in quantum-related domain. And so that went on to the PhD, which was also in Cambridge, which was again a different application of the Josephson effect for, making devices in nanoscience and technology, but then using, of course, quantum. So it sort of, started, I would say, several, now I don't want to take exact number of years, but then it was a long time ago, and it has continued ever since, right? So exploring different applications and different areas within quantum.
Okay, yeah, that's great. So since you mentioned applications, could you elaborate on some specific and unique properties of quantum systems that sort of make it useful?
Sure. Yeah. Well, one of the main things in quantum domain is that if you do a measurement, then of course, you change the system in some sense. So you leave a mark. So you cannot just copy. So for instance, we are used to all these photocopies of various things, Xerox and so on, but then that is something you cannot do for a quantum system. It's called the no cloning theorem. So you cannot clone a quantum system completely. So then that comes in as a very handy thing in, information transfer. So if you're trying to do some secure transfer of information between two agencies, and if a third party tries to copy it, keep a copy for himself or herself, that will be known. And so then, it's one of the main applications of quantum secure communication, of course. Then another one which comes to my mind is what is called quantum superposition. So, that is again a very counterintuitive thing. So, we are used to a switch being on or off usually, but then in superposition, you can have a little bit of on and a little bit of off at the same time. So you can form, in fact, an infinite number of states where you can have a little bit of this and a little bit of that instead of just one or the other. And this gives us access to this large space where all these quantum algorithms work and makes quantum computing possible. So, so superposition, no cloning. Then there is something called quantum entanglement. Maybe you have heard of that. This is a correlation, right? So it is very quantum in nature. It doesn't happen in classical systems. And there also it comes in handy for keeping information secure. So these are some of the things which don't have a parallel in our classical world and find themselves useful in these very cutting edge applications.
Definitely.
Yeah.
Definitely. Okay. So your work has currently, your work has been mostly in the quantum communication domain. Is that right?
Well, we tend to work on, both the fundamental science and the applications sort of
Mm-hmm.
side by side. So so we are studying various properties of entanglement, quantum measurements, and so on. And in the meantime, we are applying them to quantum communications, but also quantum computing. So we are working on, different applications, but communications, we have been doing many things in that of late.
I
Yeah.
see. I see. Okay. So for the uninitiated, could you just elaborate on what quantum communication is and say what
Yeah,
RRI has been doing right now in
sure.
this field?
Yeah, so I mean, it's of course a very detailed topic. So I'll just try to make it, as simple as possible for the discussion. So essentially, the idea is like, you and I are talking to each other, and this is something, you're recording, so it's going to be available for people to see and hear and so on. So there is nothing, secret about it, right? Like we intend this to be known to other people. And so this is what is usual communication, telephone or cell phone and things like that. We usually don't have any secrecy associated. But suppose you are actually a bank, and I'm actually trying to buy something online, and I give these, details of my bank account and so on. And that is something I don't want a third party to know, because of this reason that, you don't want whatever little money you have as an academic to go to someone else. So there are, examples here where, or if I'm voting, right? That's a very common topic all over the world. So you're voting for, whichever candidate or party to come to power, right? And so then in your elections, so you do want your vote to go to the right one, and it shouldn't be tampered in some sense. So these are all examples of, things we do sometimes daily, sometimes once a year or whatever, which is strategic in nature. So this is strategic communication. So you don't want the third individual to know anything about it. The other example would be the defense, of any country. They are doing all these, communications with other countries. They don't want a third country to know it if they don't intend that way, right? So securing our borders and so on and so forth. So strategic communication is done traditionally by what is called cryptography.
Mm-hmm.
So, the idea being that I'm sending you some information. Let's say I love RRI is the message I want to give you. But then I don't send it in these alphabets. I sort of encrypt it in what is called a KEY key. So, let's say I just replace them with the position in the alphabet. So that is the Varnam cipher. It's a very common, traditional old way of doing things, but then it's still popular. So, let's say I is whatever, 13th or 14th alphabet in the English language. And so I just replace it with the number equivalent. Okay. And I send it to you. And you know that this is the methodology I have used. So you know what to do to get back the number. So essentially I convert the alphabet to its, in some sense, number equivalent. And I give you some, and then I, give you something which has not, it doesn't seem like it has anything to do with the message I wanted to send you. So to a third party, he or she won't be able to follow what I'm doing. Okay, so this is cryptography. And traditionally, one of the common ways of doing this is basing this on the mathematical hardness of a problem. Okay, so I mean, I actually want to ask you a math question. Let's say, so what is 3 times 7, for instance?
Mm-hmm. 21.
Yeah, you know that, right? But then if I tell you, give me the prime factors of 1, 1, 3, 4, 7, 1, you won't be able to do it that quickly, because multiplication and factorization are reverse problems, right? Yes. So if 3 times 7 is 21, 3 and 7 are the prime factors of 21. But then if I give you the factorization problem, it's a much harder problem than multiplication. And so my RSA algorithm, for instance, is based on this knowledge that factorization is a hard problem. But now, the fact that it is hard is actually dependent on who's trying to solve it.
Solve it, yes.
Yeah. So now, I mean, it's not a human thing I'm saying, but then it's more like, does an algorithm exist to crack the factorization algorithm, And so maybe at the moment it is a hard problem for classical machines, but a quantum computer will run what is called Shor's algorithm. Okay. And so that algorithm, which was developed by Peter Shor, has actually a way of solving factorization which cannot be done on a classical computer, but on a quantum computer it becomes an easy problem in that sense. So the hardness of a problem really depends on your ability at the moment, as a community, to be able to solve it. So because we don't have the ability, we feel it's hard, but maybe some genius comes along, and this happens a lot, right? Like 13-year-old doing something, you hear this all the time. So somebody comes and says, okay, this is a solution to the factorization problem. That can happen. There is no theorem, okay, which tells you that it is a hard problem. It is just currently we don't have the means to do it. So this sort of a thing is an issue, because quantum computing will be able to solve certain classes of problems which become a threat to our cryptography as we know it in many ways. Okay, and so we need a solution to that, because quantum computers will do many things which we want them to do. So we don't want them to become a threat for something like security. So we need a solution coming also from the quantum domain. And that is what is called quantum communication or quantum cryptography, where we are using laws of quantum mechanics itself to kind of, solve the problem. So we are changing how the key is distributed, not by using mathematics, but then by using, let's say, Heisenberg's uncertainty principle or entanglement, things like that, which are primarily quantum. And this gives you a new way of doing key distribution, which is going to, counter the quantum computing threat, so to speak. And so that is quantum communication, really, in a very holistic sense.
That's really nice. Thank you for describing it so nicely.
You're welcome. Yeah, it just gets difficult beyond the point if I don't really get to, but then of course this idea is to just give you a flavor for how quantum mechanics is playing a role in this communication. So the idea is that the communication part, of course, is standard. It's the key, KEY key, which is distributed, which is done using this quantum principles. So that is quantum communication. But having said that, if we talk about quantum key distribution, so there are different protocols that are followed for doing this. Some are based on uncertainty principles, some are based on entanglement, so on and so forth. And there are reasons for that, which we can get to. But having said that, in our lab, we are working on different aspects of quantum communications. Of course, we are working on the key distribution problem for sure. We've come up with a new way of doing a new protocol that we came up with a few years back, which has, so one of the things that one needs to look out for is that this key that you're generating, is it long enough or is it fast enough in some sense? Because you want to encrypt your information with it and send, right? So how will you, so the rate at which the key is generated is important. If it is just one key per second or something, then it's not very useful from a practical scenario. So we want to increase the key rate all the time, okay? And the other thing we want to do in the community is actually lower the error associated with it. Because, if I'm sending you something, maybe there is some reason why it just flips. So things like that happen. There are classical ways in which error can be generated in any experiment. Yes. Also, you have your eavesdropper who can kind of try to still steal your info. And then that will also lead to an error. So we need to ensure that the error is up to a certain threshold, because beyond that, it is not a good candidate for the communication that we want to do. So increasing the key rate and lowering the error rate are two long-standing goals of quantum communication. So the protocol that we have developed actually has a higher key rate and lower error rate than the previous implementations of that using the type of source we are doing. So that was something which is very nice, because it was in fact India's first published result in quantum communication.
That's amazing.
Free space QKD. This was the first result. It was published in a journal called Physical Review Applied. But anyway, for the current purpose, it was received very well. Yeah. And so we are working on different types of protocols, but our aim is to increase the distance of communication. So of course, I can talk to my student in the lab. That's what we end up doing when we have lab-based demonstrations. Alice and Bob are both in the lab. So that is nice for what is called proof of principle, but practically you want it to happen over long distance so that you can have the communication happen over long distance.
Like
so long distance, so this long distance in quantum communications is our, one of our thrust areas. And in that, we are working on, increasing the distance by using a satellite as a trusted node. So if I want to send a key, a quantum key to, let's say, my colleague in Canada, I will not be able to just send it in free space because I won't see him. Earth is round.
So there's no
So
line of
beyond
sight.
a point, yeah, you don't have line of sight beyond a few hundred kilometers. So you need to come up with out of the box solutions. And so satellite is one of them. And so satellite-based quantum communications is something that is picking up a lot now globally. And so our project is the first one from India, which is pursuing this, effort. So this is one of our, big projects in quantum communication. It's in collaboration with our space agency, which is called the Indian Space Research Organization, or ISRO. And so we are leading this project. So this is one. Then the other thing we are trying to do is the reverse problem. So one is, so satellite-based quantum communications is good. It will help in increasing the distance. But beyond a point, people like you and me may not be using it all the time because, it's not like we will have a satellite for ourselves or, that won't happen. So if you want to use some security for yourself, one thing that you are using all the time maybe is a cell phone. Right. So you want some chip within that to generate quantum keys. So a chip-based QKD is what we are also pursuing in a different project using integrated photonics and in collaboration with our colleagues in Italy. So this is another thing. So these are kind of, that's more like for common man, whereas the satellite one is for enabling the country to become, quantum enabled and secure. The other thing we are doing is what is called quantum teleportation, maybe something that you've heard of. I mean, teleportation is something which is much in public domain in science fiction, right? So if you may be too young to have watched Star Trek and so on, but then maybe you watched some movies, yeah. So then, this beam me up, Scotty, that is the famous dialogue from Star Trek. So this is how teleportation is perceived in science fiction, but in real science, human beings don't get teleported. It's more the the state of the system, which is transferred to another system. The systems remain stationary, the state is teleported. And we are doing this over, both in the lab as well as over long distance, because it's another way of quantum communication. And the fourth thing which is coming to my mind is another project which we are doing, which is on generating random numbers. So maybe that also, so random numbers play a crucial role in simulations of biological systems, weather, as well as cryptography. That is the fundamental thing required in cryptography. So we are coming up with a new way of doing that using what is called device independence. So these are our main projects right now in the communications domain. And I could go on, but maybe you want to say something.
No, it's really great to hear about all this. And specifically to the random generator part, I just wanted to say that, yes, as of today, we just use the pseudo random functions. So
right.
Yes,
it's not, the pseudo random numbers are not really,
really random,
cryptographically secure. So you want something where the randomness is generated not, so pseudo random number is generated by an algorithm, right? Which is running on a computer. So suppose, you are my adversary, let's say. So if you know that, you can hack the computer and then you will know whatever, it won't be random anymore. But then you want something, the source of randomness to be independent of the device. Because, I mean, all this leads to some philosophical questions also that, the security and so on. It makes you think that, we trust each other less. And that is why all these things are being done, right? Like to keep things secure. But then, beyond a point, people like us, we are not responsible for this mistrust. It's more like we're trying to come up with ways to ensure that things remain secure. But people say, it's like the world is going to more and more not trusting each other phase, which is actually true. So we cannot help it, but we need to ensure that we don't get affected by it. So this device independence is another level. So you don't trust who's making a device even. So you want to come up with a way of generating randomness from correlations which exist irrespective of whether the device has been compromised. And so that is what we are working on actually. So it's a very nice topic.
Yeah, it is. And even in computer science, that's what they do, right? They want to make the trusted base as small as possible so that.
Exactly. So at some point you want to even get rid of it is the idea.
That's
so you
true.
Don't want anything in your system to actually be dependable. So even if you were living in a scenario where everyone is your adversary, still these correlations will work to generate randomness. That's the sort of goal.
That's true. That's really interesting. Yeah, thank you for sharing all of that. So just looking at, the kind of projects that you've been working on, it sounds like you've dipped your toe in a lot of different sciences, including, say, material science and even, say, satellite communications. So how important do you think is expanding one's research to other interdisciplinary fields? Because these days I just see this siloed nature of work. So what do you feel about that?
Yeah, that's a great question. And of course, as you have rightly pointed out, I myself, of course, I am of the opinion that it's good to actually have, a broader knowledge base, because at some point it helps one in connecting things. If one has actually some work experience in a certain domain, then it helps you in connecting it to another domain easily. Otherwise, of course, it is more based on what you read. But then, there is one has to have a balancing act here. So you cannot just keep changing things every year, for instance. I mean, so if you feel that today I'll do biology, next year I will learn physics, and next year I will do chemistry, then you don't really, you have to, of course, develop some knowledge before you move on to something else. So, so one has to do this in a way that, okay, so I actually now have a good understanding of this field, then maybe I want to understand this better, because then I can do something which connects the two. So far as I'm concerned, as you may have noticed, I've worked on superconducting devices and things like that for my PhD, and as well as master's projects and all. And then I shifted to quantum optics, another realm of quantum, right? So this was more solid state, that was quantum from the optical point of view. And so, of course, now I can have a good understanding of devices as well as light. And of course, the idea is to merge them, because ultimately you need to merge both solid state and optics to go to what is called quantum interfaces. So I think this has helped me. But then, having said that, I'm lucky that I actually got the opportunity to explore multiple things as I moved along. And it may not always happen, but then if you want to do that, then the best time to do it is before you sort of have a faculty position, or settle down making your own lab, because after that it becomes difficult to do too many diverging things, because you want to build up in a certain area. But before that, given the opportunity, it's good to explore during the project positions or postdocs and so on. So that is how I have yeah, material. I mean, my PhD was from the Department of Material Science. So in some sense, this nanoscience and, deal with a lot of material aspects of the problem. And I took it a little bit to the extreme in one of my postdocs, where I worked with the paper industry to make paper whiter, but then while retaining its being thin at the same time, because the cost goes up when your thickness goes up. So this was a South African pulp and paper industry. So applying sol gel techniques to do that, and that was a little bit of a diversion from the quantum theme that I've had all along. But it was very nice, because I got an exposure to something which is otherwise something I may not have done, as I moved along a certain quantum theme. Yeah.
That's really interesting. Yeah,
Yes.
I'm just imagining being in the paper industry, and then if you think about it, it sounds very different, but then when you boil it down, it's all physics, right?
Yeah, it's all physics. And so then, that is a realm of physics which doesn't come into my everyday existence that naturally. I mean, as a physicist, I mean, because I'm working on quantum optics or devices, and these are all more related. But that opportunity came along, and it was a collaboration with the Cavendish Lab. So I actually went to Graz in Austria to the paper industry to do some knowledge transfer, and figured out how industry functions, which is kind of different from academia. And so, just to get a flavor for how the industrial people think, which is not how we think usually, to be honest. So it was a good exposure, I think. Yeah.
Yeah, you mentioned about how you sort of explored all this before setting up your lab in RRI.
Yeah.
So how was your experience, in the first few years? Because I believe you were the first few people to actually set up this lab. And
Right.
where do you think the push came from? Because quantum is only like a buzzword now. So how did it all come about?
Well, for me, I mean, I'm much older than the buzzword. So I've been working on this for more, 22, 25 years, whatever, so it's been a long time that I've worked in different aspects of quantum. So it was natural. I mean, when I actually wanted to set up a lab, it was natural that it would be in this domain. But I did realize that, we were one of the first, if not the first lab, which was working only on quantum information things. So now what is happening is people who are not traditionally working on quantum areas are also trying to find synergies, so that, because the quantum thing is becoming a bigger, word as we go along, as you say, buzzword. But then when I started, it wasn't the case. And so it was, in fact, I have had questions like, will all this ever be real, in our lifetime? Do we really need a quantum computer? Would we ever get one? And so I don't think it was very, the circumstances were very conducive to setting up such a thing in India at that time. But then, of course, it was good to have support from the institute to, for the initial start, because after that we have been, again, one of the first people to get a lot of extramural support very quickly. But then in the beginning, the institute support was crucial. And I think, one of the biggest things which I always acknowledge in the setting up of my lab is, the people who are not really even academic, who belong to, let's say, the civil engineering department of the institute and the electrical group. These are people who really came together and helped in setting it up, because ours was the first clean room at RRI. And so we had to write a 100-page document to get that approved. And so a lot of help came from the support staff, I would say, because they also were equally enthused about such a lab being set up. And so I definitely cannot say that it was now if one wants to set up a lab of the same type, I think there will be a lot more encouragement, which wasn't the case 10 years ago. Yeah.
Yeah, speaking of the encouragement perspective, in 2020, the Indian government allocated over 8,000 crore over 5 years for quantum. So being someone who has worked in this field for so long, so how do you feel about the quantum landscape in India in general? Like, I mean, I'm sure it's much more conducive now.
Yeah. So, I mean, this promise of resources has led to a lot more happening in the country, I would say. So, when, we have done many things, but then now there are other groups which are coming up, which want to contribute to similar efforts. And then, new groups have started. So there is a, nice ecosystem that we have. In academia, there are quite a few, labs in different, systems, let's say. And then, of course, in theory, we have always been very strong. So our theory contributions have happened from much before this promise of resources, because theorists don't need as much resources, as experimentalists do. But then without the experimental thing coming up, we really do not see ourselves well poised to make, contributions, long-lasting ones. So I think now it's very nice because, more promising and more challenging experiments can be established with such resources. And then, of course, we have a lot of theory support as well. But then one of the downsides to all this, because I never say anything which, it's always holistic in my mind, that nothing is ever always positive and always negative. There's always a bit of both. And so while all this is very nice and, it will lead to us playing a very important role in this field, let's say, but we have to play this a bit carefully, because we don't want to necessarily just end up doing duplication of resources. We want to have a good amount spent on novel ideas. And so in that sense, the little problem that is there is, lots of people who may not be from this field suddenly jumping in and claiming that they want to. So then this becomes a little tricky about the distribution of resources to the right set of people. And of course, I'm sure people who do that are thinking about all this. Our job was to essentially come up with a draft for the national mission. So I contributed to the draft for it. And so over the last couple of years, it is moving ahead, but we wanted to start now. After the declaration, we've not yet formally started the mission, so to speak. So hopefully it will start soon, and hopefully it will start with a way where, things are done to enable those who deserve it and so that we can have a niche presence. While I'm, of course, in this inter-ministerial committee that has been formed on quantum communications, I'm representing academia. And so my job is to bring synergy across institutions and come up with a roadmap for quantum communications in the country. So I'm trying to do that to the best of my ability with colleagues, So I mean, there is a lot to look forward to, but I sincerely hope that it is sort of structured in the right way, which is important for it to, succeed. Yeah.
Oh, it's great to know that a mind like yours is over there thinking about all these policies. So
I try do what I can. It sometimes gets a lot because there are lots of things which I find myself in various such roles, right, both nationally and internationally. But I think it's my responsibility to contribute to that, so that at least I can ensure that certain things are done in a certain way. At least I can have that opportunity to make my point, right? So being a part of these sort of organizations and meetings is important, I think. To have the academia say in everything,
Yeah, because I guess academics and science is one thing, but sort of putting that into policy and translating it into
that's a whole new ballgame. Yeah.
Yes, definitely. Yeah, that's really interesting. So you were saying how there are all these people who want to jump into quantum computing and just in the quantum field. So would you suggest any kind of, say, resources for undergrads who want to contribute in this field, or is there a specific way where someone can start working on quantum in their early days, or say at any time at all?
Yeah, I think definitely. So, I think when I say all these people, of course, the students should be excited by this. Aspiring, it's always the young generation is the one which we always want to encourage, because they will, and that is how we build up our, basically our human resource development is very important for India. So having said that, in the domain of quantum, of course, we don't really learn quantum physics up to a certain point in our degrees and so on. But then it's one of those areas in which not all the contributions are coming only from the physics perspective. So, if somebody is, developing, or pursuing an engineering degree, let's say, in electrical and communications engineering or something, so then they can always find some useful things to contribute towards a bigger program. So there are things that one needs to do which require engineering capability. Then there is also things which require mathematical ability, all these algorithms and so on, and post-processing algorithms that we have for QKD. So these things, there is a lot of scope, and of course, but then the person has to be very motivated and willing to learn and so on. But then there are lots of things which one can do even while pursuing a degree. It need not be always at the level of solving Schrodinger equation or something like that. That is a misconception. So there are many things to do which are allied, jobs or roles, let's say, which contribute towards the big picture. So even in satellite QKD, now that is a fascinating area, because we need people who have expertise on atmospheric science. We need people who have expertise on telescopes and things like that, maybe from an astro background. So even our team consists of different types of people, and not all are from physics background even. So in some sense, this is something this field sort of lends itself to a lot of interdisciplinary growth. And so I think an undergrad, and I have had interns who have worked on parts of problems very successfully, some not successfully, but then it really depends on it does depend on to a point also on your own motivation. But then of course then one does PhDs in the field, that is you can have a long-standing contribution, right? So yeah, it's one of those fields in which you need not have a very set of things that you need to do.
Yeah, that's really interesting, especially considering that just recently on April 14th we celebrated World Quantum Day. So I'm sure a lot more people would have been excited by the prospects of it. Were you involved in any of its activities? And what do you
Yeah,
feel
yeah.
about one day for this field, right?
Yeah, I of course feel very strongly because I mean I'm actually representing India in this World Quantum Day network, right? So then it's while it's we actually have this tagline, every day is Quantum Day. So in some sense, of course, every day one can make efforts towards quantum, but to have one day earmarked is nice because otherwise we tend to. I mean, it's like a birthday, right? So one day being a birthday is useful during the year because everyone remembers you and sort of you feel thankful for being alive because others are wishing you. So it's something similar. So having a day earmarked is a great idea, I think. And of course, this time what we had is, one of the events which sort of happened globally is what is called Quantum at School. So this different countries participated in that in their own countries. People organized events for high school children to get more to teach them something about quantum, to get them excited, and so we also organized Quantum at School from we didn't organize it physically still because of the still we are doing things a little bit more online. So but then RRI organized Quantum at School, and we had experts in the field give little talks. And so we had high school students attend that, lots of interesting questions. So, trying to get this excitement to even younger minds, because I think, that is where you are more open to new ideas. As one
That's
grows
true.
older, we tend to get more set in our ways, and we close our minds a little bit is the thing.
And the cynicism
So,
grows.
yeah, so that exciting high school children is always of course it's challenging because you have to express the thing in a way that they can relate with it without getting too bogged down by too much sophistication. So but it went very well, our Quantum at School event. So that happened, I think, on the 8th of April. So as a lead, because 14th was a national holiday here, so it was also, I think, just before Good Friday, right? So then, in some sense, we had it the week before so that we could have more students attend. Yeah.
Okay.
So it was very
That's great.
successful. Yeah.
That's really interesting to know. So
Thank
thank you for sharing all of your experiences. Now I would like to sort of pivot to a more sort of personal question in terms of what sort of made you move back to India, and what were those factors that influenced it? Because I understand you were in international waters before this.
Sure. Yeah. So I was away for almost close to 12 years actually. So it was it was a decision which took some time because, when you are away for that long, you tend to sort of get a little bit settled in. Not everything is the same in every country. So, but then my decision to move back was, both personal and professional. So personal in the sense that, I have family. I had, unfortunately, not everyone is around at the moment, but then with family members who are, getting older. And so then you want to be close to them. Doing that was one of the reasons. But then the other thing, of course, was a bit more of a nationalistic thing that, having learned all these things and, done certain things, you want to do it, in your own country and so on. So to set up something and see it succeed in India itself was one of those motivations as well. So it is a combination of both really, which sort of helped in taking that, making that move, right?
That's interesting to know. Yeah. So did you have any, say, specific challenges or any kind of learnings that you might want to share? Maybe regarding the move, maybe regarding to your whole, career so far.
Yeah. Yeah, it's never it's always an uphill task, right? So nothing is straightforward. As it's not like you just come, you set up a lab, everything is there for you, and you just do good science. It's never like that. And of course, one of the challenges that I had was also the two body problem. So both my husband and I wanted to be in the same location as well, and so of course we have managed to solve that. Traditionally, for several years we've been doing that. So, but then, and now we've done that. So he's also in Bangalore in ISC. But then it's not, there are many things in the, essentially in your environment, which are, some of it is very encouraging, whereas some of it is not. Of course, one of the things which never helps is our particular gender, right? So, I mean, we do belong to a certain gender, which is traditionally, not seen to be playing the leadership role. And so it's somehow been there. This bias does exist, and one of the things is, when you do something in a good way, and when you achieve certain things, then of course it takes a bit more effort to get that recognition, I would say, being of a certain gender than it does for the other. I mean, as I always say, that for the other gender, it is being ambitious. For us, it would be like being attention seeking. So it's the same characteristic traits may be termed differently depending on which gender you belong to. And so also in India, we have this tendency of, associating a leadership role with a certain age group as well. So you have to be above a certain age and with some different color in your hair, let's say, so that you can be considered for that. And I've traditionally been opposite to that, always, not conform to those expectations, let's say. So this is one of the other things. And of course, the other challenge that that we face is, about students, right? So, I mean, we would want students to remain, of course, to a certain extent, they should contribute to efforts here. But then there also I've seen that, there can be like a lot of pettiness and negativity can happen. Sometimes it grows, and then there is, I've also seen female students sometimes prefer male supervisors. Maybe they feel that there is some sense of security associated with that, which is of course not quantum. And it's not proportional to your achievements, because of course then there is no comparison. But then, so these things are there, and these things one cannot change in a day, but all one can do is, just try to, I mean, I just try to block out anything and everything which brings in such things, and just go ahead. And so I've not traditionally been a kind of person who likes to chat a lot and waste my time and in discussing things with people in the middle of the day. So I've not been like that. So I continue doing that, and that helps, I think. And now beyond the point, it is difficult to actually ignore. And so one has now reached that stage that it is.
But I guess just you being there, you're breaking some barriers and setting a great example for
which
everyone
is the
else.
hope, right?
So
yeah.
that is always a good thing.
Absolutely, yeah. And so this is the point. So when one is able to actually reach a certain stage, in spite of these, of course, existing things which cannot change in a day, then of course it sets a good example. And I'm very happy that there are some students that I have who are very inspired by what we have done, and they want to contribute. And so you will see both sides of the coin. As I said, nothing is always
Definitely.
good or always bad, and so one has to try and somehow filter out the goodness in everything and then move ahead. Then one succeeds better than if you just get affected by everything that is not up to your expectation, right? So this is how
that's understandable. But like you said, with the whole holistic approach, there are always some pros and cons, and
there's always going to be
and even if we are making progress 1 quantum per day, that's good enough.
I know, it'll together it can form the the computer. So every qubit matters, right? So
every qubit
matters. one qubit has been added, so now we are at 50 or 75 or whatever. But then it has taken several decades, right? So it's never easy. I mean, you took a great example, because why is it not easy? If you put many qubits together, then they sort of undergo a phenomena called decoherence, which means that they interact with the environment and their properties degrade, let's say. So it's the same thing with human beings also, right? So you want to ensure that you don't suffer from decoherence, but you keep adding to your list every day of things you want to do and want to achieve, right? So then decoherence-free subspace, it's called, is what we aim to be, right, in life as well. So
very well put. That's a new way of looking at tiny progress every day. So
absolutely,
that's really interesting. I think this is great. I think we can we can stop here with saying, yes, every qubit matters. And once again, thank you so much, Professor Urbasi Sinha, for taking the time and actually talking to us for this interview.
You're most welcome, Neha. And I think you're running a great effort here, and trying to sort of, bring people in on the same platform. And I wish you all the best with your, endeavors, your, studies, as well as, this effort that you're a part of. So it was very nice being a part of this, discussion. Thank you so much.
Same here, Dr.
Yeah, thank you.